Welcome students. In this video we are going to talk about non-homogeneous problems. Yes, and for this particular lecture, see, I am choosing a particular kind of problem, but it doesn't have to be that. So essentially the things which I am going to show you with slight modifications, you can do similar sort of things for wave equation, okay, Laplace equation, and heat equation. So essentially what I am saying is, if you know how to solve the homogeneous problem for those three equations, you can use that idea and you can have use this particular tricks which I'm going to show you to solve the non-homogeneous, let's say, wave equation, or non-homogeneous Laplace equation, or non-homogeneous heat equation. So this is not particularly of any particular equation, this is just for a non-homogeneous problem. So let us first of all understand what's happening here. See, what is the relation between homogeneous equation and non-homogeneous equation. So let's just say we start with the equation LU equals to 0, let's call it 1, and there is another equation LU equals to F, let's call it 2. Okay, now you see what is L here, L of U, it can be this thing uxx plus uyy. I'm just writing two dimensional, okay. It can be utt minus uxx, okay, or it can be ut minus uxx, okay. So it can be Laplace, it can be wave, or it can be heat equation, Laplace, wave, and heat, okay. So any of that is fine. Essentially what I am doing here, this is valid for any. So let L be linear in U, essentially linear in U, okay. Then what happens is this, let's say that I want to find out. So the question is this is assumption. Of course, you see, all of this is defined in some domain and all. We are not really interested in that. We just want to look at the trick which works, okay. See, L is linear in U, so as you can see, all of these things are linear in U. Yeah, Laplace. So this is okay. L is not Laplace. L is, maybe I can write it like this, L cap. Some operator, L cap. Okay. Now the question is this. See, can we find the solution of U? Solution means all possible solutions of U. Solutions of 2. Sorry, 2. Okay. So how do you do it? So let's say that we know how to solve this problem, right? Yeah. Let us assume that we know how to solve this problem, and let W solves 1. So you have somehow found out that there is a general solution, W, which solves 1. Okay. So this is a general solution. General solution is all possible solutions of 1. Is it okay? Right. Now, if, okay, V solves 2. V solves 2 means, see, now you will say that we are trying to find solution of 2. Why are we starting with a solution of 2? Essentially what I am trying to say is, we are trying to find out all possible solutions of 2, if it is possible. We want to find out so the variety of solutions, whatever solutions is possible to find. Okay, now what we are saying is this, let's say by some hook and crook, we don't know how, but right now, but somehow if we get to know that there is one solution of 2, okay, so what can we do is, we can take that solution V. So let's just call it V. Then, so you define U, which is W plus V, okay, solves 2. Okay, so you see, in that case what will happen is this, you get other solutions also. See, if you take V is already solves 2, right? And now W solves the homogeneous problem. Okay, so this is the homogeneous problem part, and this is the inhomogeneous problem part. Homogeneous problem, so you see, W is a general solution of 1. Clear? So W content is not a single solution, but a family of solutions. Here this is just a single solution, but you add it up and that will give you a family of solutions. Okay, so proof is very easy. So proof, we are not going to do it explicitly, but I mean, there is nothing to do here. So L of U, if you take the operator L cap of U, okay, so that is what, it's a linear. Yes, so it is L cap of W plus U, so which is nothing but L cap of W plus L cap of U. L cap of U. Now you see, L cap of W is 0 because W solves the homogeneous problem. So this is 0 and that is F. So this is essentially F. Yeah. So you see, this solves the problem. So that's the idea. See, this is the relation between the homogeneous and inhomogeneous problem, is that once you know how to solve the inhomogeneous problem, just one solution, and you know how to solve the homogeneous problem, you can just add it up and get more solutions out of it. Clear? Okay, so now let's look at some tricks of how to solve those. Yes, now again, now what we are doing, we can do it for the heat equation, we can do it for the wave equation also, we can do it even for Laplace equation. Okay, so let me do this part, but of course with some modification. Please understand this, yeah, under some modification. Okay, so first example, let me do the first example here. So let's start with the heat equation, because this is the last part which we did heat equation, right? So let's look at it. Ut equals to uxx. There is a constant times uxx, but let's just forget about that. Of course, you can put it, absolutely no issues here, but I am not going to put that part here. So f of x, and this is x is between 0 and L, is it okay? And t is positive. This is what we are assuming here. And we need to have some initial condition, which is at t equals to 0, u of x0. Let's just say that the initial temperature of the system is given by f of x. And on the boundaries, we are saying that the two sides of the boundary are, kept at the constant. So the two, ends of the this thing rod is constant. Okay. So what is it? It is u of 0t equals to a, and u of lt equals to b. Is it okay? So this is for again time t greater than 0, and this is for 0 less than x less than equal L. Yes. Okay, now the thing is this, we need to find a solution of it. Okay, so the solution, how to find it? See, what we'll do is this. Again, the trick is this, we have to somehow reduce this problem to the homogeneous problem, but how am I supposed to do that? Okay, so let's see. See, what we'll do is this, we are trying to find try to find a solution of the form u of xt equals to v of xt plus capital U of x. Is it okay? This is what we are assuming. Yes. See, the thing is this. This function here, the non-homogeneous part, generally speaking, it should look like function of x and t, right? But the thing is, this particular problem, it doesn't have that. It only has that it is just a function of x. What I am doing here, it can also work with just a function of t also. If it is just a function of x and just a function of t. Let's say, if it is just a, so if f of x is replaced by capital G of t, okay, then you replace this thing with t. Is it okay? So essentially in this case, capital U of x will become capital U of t, and then you can do the exact same thing. Okay, right? So this method which I am showing you only works when the non-homogeneous problem. This is called the source term, when the source term is either a function of x or a function of t. Is it okay? Right. So u of x equals to v of xt plus capital U of x. Okay. Now if you substitute of substitution of u of x, so substituting one has see, and of course I am assuming that u is sufficiently smooth. U is in C infinity, let's just say. Okay, so if you substitute it, what happens? Then we have that u of t is equals to v of t, because this is independent of t, so it becomes 0, it taking derivative. And moreover, u of xx is nothing but v of xx, right? V is also smooth, so we are also assuming v is C infinity. Okay, plus the derivative of this thing u double prime of x. Yes, is it okay? Right. Now once that is true, you see what we'll do is we'll substitute this thing. So in our original equation, let's just call it 1. So substitute again from 1. What do you get? From 1, you see we get that Vt. Okay, this is not substitution, it's differentiating. Sorry, differentiating. Okay, now Vt is nothing but this is equals to Vxx. So you see it is Uxx plus f of x, right? Uxx is Vxx plus capital U double prime of x. Okay, plus that f of x is there, f of x. Is it okay? Huh? And so ut is equals to this. Now you see the choice of capital U, yes, that is on us, right? So we choose it in such a way that V solves the homogeneous equation. Okay, so choose capital U in such a way that it solves the homogeneous wave equation, heat equation. Okay, so what does that mean? It means that we will take, you see, so that is u double prime of x plus f of x will be chosen as 0. If we choose this part as 0, you understand, see, f is given to us. We are trying to find a u such that u double prime, capital U double prime plus f is going to be 0. If we have something like this, then you see Vt equals to Vxs, that will be your parabolic problem, the heat equation, which is the homogeneous equation. But again, you see, homogeneous equation is fine, but the thing is, these boundary conditions, these are the boundary conditions, right? This is the initial condition. Okay, but the boundary conditions we need it to be 0, you see. Yeah, but here it is a and b. So what am I going to do here? Okay, so let's see here, u of 0t is a, so a is u of 0t, clear, which is equals to v of 0t plus u, capital U of 0. Okay, so you see, if we take capital U of 0 to be a, if we take capital U of 0 to be a, okay, that will imply that v of 0t is going to be 0. Is it okay? And if we take again, b is what is it, u of lt, right? So let's say that is v of lt plus capital U of L. Okay, now if I am taking capital U of L to be b, so capital U of L to be b, then you see v of lt is also going to be 0. So basically we have a boundary condition which is 0. Yeah, so this is very, very important, right? Why it is important? Because you know, in the last video, if you go there, you see that we know how to solve this sort of problem for a homogeneous boundary, so homogeneous heat equation with a 0 boundary condition, right? That is important, and this is how you can do it essentially. Okay, right. And of course there is another condition, the initial condition. Initial condition, what does it say? It is saying that f of x is u of x0, and that will be v of x0, okay, plus t equals to 0. So this is capital U of x. Okay, so this is another initial condition. Okay, let's understand this thing. Let's call this 3. Okay, now you see, this is a second order ODE essentially. There is nothing to do with PD. So this is a second order linear ODE, right? And of course we can solve it, absolutely no issues. This is very easy to solve it. Yeah, let me write it down. So from 3, what do you get? We get that capital U of x is nothing but a constant a, okay, plus b minus a. Okay, see, u of 0 is a, sorry, this is a, right? This is a, it's capital B, capital A, capital B, this a and b. Okay, so this is a plus b minus a, x by L plus x by L, and then 0 to L, 0 to eta f of xi d xi d eta. Is it okay? I hope this is correct. Okay, fine. Minus 0 to x, okay, and then 0 to eta f of xi d xi d eta. It's okay. Yeah, so this is a second order equation. Of course it looks a little complicated, but what I want you to do is basically please check this part. Yes, check it. So generally speaking, see, I am writing it in a general form, right? That is why it looks so complicated. Let's just say in general, for math, problem purposes, this problem f will be given to you. So let's say u double prime x equals to, it will be like u double prime x plus the capital F will be given to you. Let's just say that is something exponential x equals to 0, right? Yeah, now you do realize that you can solve this problem, right? It is not a very difficult problem to solve, yes. Or let's say if sine f of x, capital F of x is sine, so in that case u double prime plus sine equals to 0. You can solve those problems, right? So that's what I'm trying to say. It is not very difficult thing to do, but the thing is, since I'm writing it in a general form, this formula is a little complicated. Okay, now once you have this capital U, now what is your, or now hence one deduces to the following. Okay, what does it deduce to? Let's understand this thing. Vt equals to Vxx, this is true. Yeah, you see, Vt equals to Vxx, this one, because this part we are assuming it to be 0, right? So for u which looks like that, you see, for u which looks like this part is going to be 0. So Vt equals to Vx in this interval. So between 0, L and T positive. Okay. Okay. What is the boundary condition? Boundary condition is 0T equals to A, LT equals to B. You see, boundary condition V is basically 0 and 0. Okay. So V of 0T equals to V of LT is going to be 0, T positive. Okay. So this is the boundary condition, the new boundary condition. Okay. What about x0, the initial condition? X0 is this. See from here what do you get? V of x0 is nothing but f of x minus capital U of x, right? Okay. Now, do you know what capital U of x is? Of course you know. Do you know what f of x is? That also you know, right? It is given. See, capital F is given and capital U is already known because this is capital U. So that is nothing but fx minus capital U, fx minus capital U of x. Let's call this something h of x, let's say. Let's call this h of x. So now you see this is for 0xl. Now see, this is a homogeneous heat equation, right? Homogeneous heat equation. And what are the conditions? The boundary conditions are very nice, homogeneous again, which is 0 basically, and there is this initial condition which is h of t. Now you know how to solve this, right? We have already you know how to solve it. So solve for v, and to get small of u, solving 1, add v to capital U. Done, right? So you see, once you get v from here, right, how do you get u? U is our solution of this problem, right? How do you get u? You get from this thing. You see, u is nothing but v plus capital U. V we already know, solving this thing, and capital U already know. You add it up and you are done. Okay? So this is not very difficult. It's just some calculation which needs to be done here. Okay, now I will show you a very, very important problem, and this problem which I am showing you, this actually works for Laplace heat wave. Okay, so the earlier this problem also, yes, this works for Laplace heat wave. Okay, no issues. So here also, of course, the boundary conditions changes. You do realize that, right? The boundary condition will change. For the wave equation, there will be an extra boundary condition here. So ut, that boundary condition should be there, right? So you have to take into account that. And the thing is, for Laplace equation you will have another boundary condition, right? So you have to take all that in account, but essentially it is this. Okay, so now this is the second problem. Let's say you have a problem like this. For this I am doing it for the wave equation. Is it okay? The thing is, I will take 3 different methods, and I will do it for 3 different problems. The first one I did for wave heat, this I will do for wave, and the next problem I will do it for Laplace. Okay, so let's say we have this equation utt minus uxx equals to h of xt. Okay, and this is for 0 less than x less than L and t is positive. Okay, u of x0 equals to f of x 0 less than x less than L, ut of x0 equals to g of x 0 less than x less than L, u of 0t equals to 0 and u of Lt equals to 0 for t greater than equals 0. Okay. Now how to solve it? Solution. See, what we will do is this. You remember while solving the problem using separation of variable, we had a bunch of eigenfunctions corresponding to x, right? So you see those eigenfunctions, let's call that eigenfunctions as capital Xn of x to be sine of n pi x by L. These are the eigenfunctions. Do you remember while we talking about the separation of variable? Let's call this. So I'm going to use this thing, yeah. And please remember, it is very, very, very important. Yes, I mean we use this eigenfunction in many different places. Yeah, and for so this is for the Laplace equation, right? For Laplace, for the heat equation, for the wave equation. What am I saying? Sorry, this is for the wave equation, right? Now let's say for the Laplace equation, you have another eigenfunction, right? You use that, so it's not an issue. Yes. So while solving the homogeneous problem, you got some eigenfunctions, right? Xn of x. Those functions are required. Yeah. So here also I am using this function. That is what you get. And consider. So basically we are saying that we are looking for a problem like this: u of xt equals to summation n equals to 1 to infinity. Okay, un of t and sine of n pi x by L. N pi x by L. Okay, where un of t is to be determined. You understand what we are doing? See, the point here is this. Let's say I want to find the u of xt, which is the solution of this problem. Let's say 1. How do I find it? Okay, right. See, this is a bunch of eigenfunctions. Yes, and we know that we can also create an Fourier series using these xn's, right? So you see, if we fix a t, just one t, then this is just a function of x. This is just a function of x for a fixed t, fixed. Okay, and then that function can be written as in terms of Fourier series of, so basically some constant, let's say constant un times sine of n pi x by L, right? Using these functions, yes. So we can write it in terms of a Fourier series n equals to 1 to infinity. Yes. Now you see, this is for a fixed t, this is true. Now if I'm changing t, then this constant will change, and this constant definitely depends on t, right? So basically when I change, I mean, run t from 0 to something, 0 to infinity, let's say, then un will also depend on t. So un will be depending on t, which is unt, and then this function. So that is the idea. Okay. So with that in mind, what do you have? And again, you see this h of xt is given, and h of xt again, this can also be written in terms of this, right? Fourier series. Again, what is it? It is summation n equals to 1 to infinity hn of t and then sine of n pi x by L. Is it okay? dx. Oh, sorry, what dx? Sorry. Yeah. Okay. So we can write it like this. Now, if we write it, then we can say that what are hn of t? This we know what hn of t is. It will be Fourier series, right? 2 to L, 0 to L, and then h of xt. This is for 1t, you can do it, and then if you consider it as a function of t, then you can write it like this, right? Sine of n pi x by L dx. Is it okay? Very simple. Okay, now we are assuming that this function, see, the thing is, this is an infinite series, right? Star. Assuming star converges. So we are assuming that star converges, okay? Star converges. Then what do you have? Then summation. So you can put it in the equation. It becomes n equals to 1 to infinity. Okay, un double prime of t plus lambda n square un of t sine of n pi x by L this is equals to summation n equals to 1 to infinity h n of t and then sine of n pi x by L. Is it okay? Where what are lambda n's? We already know these are the eigenvalues, right? So it is n pi by L. Yes. Okay. And of course this n is the n is any number, any natural number. So n is in n. Okay. Okay, so we are just putting it in the equation. Now, if we do that, and you see now, if we are multiplying both sides of this equation, yes, let's call it 2. So, multiplying both sides of 2, with sine m pi x by L. If we multiply it for m equals to 1, 2, 3, whatever, and integrating it, what do you have? We have this un double prime of t plus lambda n square un of t equals to hn of t. Right? We'll get it, right? See, the thing is, once we multiply this, you remember the trigonometric identity which we did for the Fourier series. If you use that trigonometric identity, you will see that sine only when n equals to m, that term will be there, except that everything is gone. So basically we are just writing that term out. You see, you understand what I'm saying? So that's the idea. Okay. And since this series which we assume, this series is uniformly convergent, so it is uniformly convergent, we can take the integral inside the summation, okay, infinite sum. Okay, so we have this. Now this problem, we know that what is the solution? Un of t, we know that it is a constant an times cosine lambda n of t plus a constant bn times sine lambda n of t. Okay. And then there is another part here. Because of this thing, you remember your ODE, right? It is 1 by lambda n and then 0 to t h n of tau sine of lambda n t minus tau d tau. Is it okay? Yeah. Okay. So if this is the case, then the formal solution. Therefore, what is the formal solution? The solution in this case, solution is u of xt is equals to summation n equals to 1 to infinity and then this one an cosine lambda n t plus bn sine lambda n t, okay, this part plus 1 by lambda n. Lambdas are given like this, a this one n pi by L, so that is always there. I am not writing that always. So this is 0 to t h n of tau and then sine of lambda n t minus tau d tau times sine of n pi x by L. Is it okay? Now you see, so this is the condition solution. This is by a this thing superposition. Now if you put the initial conditions, what do you have? You have f of x, which is u of x0, right? And putting this in the equation, we have n equals to 1 to infinity and an sine of n pi x by L. Clear? See, this part I am putting t equals to 0 here. Clear? So this is what we are actually left out with. And here, what does that imply? What are ans? Fourier sine series. Ans are 2 by L, 0 to L, f of x sine of n pi x by L dx. Is it okay? And similarly, if you look at ut, so it is g of x is ut of x0, which is summation n equals to 1 to infinity bn lambda n sine of n pi x by L, right? If you take the derivative of this thing, this is what we are going to get, and then that is equals to this is equals to g, right? So that will imply b of n is 2 by L lambda n, right, the constant 0 to L g of x sine of n pi x by L dx. Is it okay? So this is your solution, and what are a and b n? For a and b n's you need to use the initial condition. Once you use this initial condition, you get your solution. Okay. Now you may ask that where are we using? So initial conditions we use, right? But we did not use boundary condition anywhere. See, this boundary condition we did not use anywhere. Okay. So why do we need the boundary condition? We need it because if you remember, while solving the homogeneous problem, these eigenvalues, they are related to this thing. You understand? With those boundary conditions only we got the eigenvalue, and then you use those eigenvalues to solve the problem. You understand? So that is how it is related. Yes. Okay. Without this boundary condition, you don't know whether they are eigenvalues or not. Of course, you can do the whole thing, but the thing is, this is how it is related. So you can see that the solution which you get, that will actually satisfy this condition also. Okay. So this is how we do it. Yeah. Now we'll do another problem, and this is for, so we did heat, we did wave. Now I will do it one problem for Laplace. Again, all of this can be done for any one of them. Yes. Okay. But the thing is, you have to make certain changes depending on the initial data. You have to change certain things, but the idea is basically here. Okay, utt minus uxx equals to h of xt. Okay, 0 less than x less than L, t greater than 0, u of x0 equals to f of x 0 less than x less than L, ut at the point x0 okay. Maybe I can do it for the wave equation itself. I am doing it for the wave equation, but exactly same thing can be done for the here the Laplace equation. Okay, so let me do since I already started, let's just do it. Yeah, you can do exact same thing for Laplace, absolutely no issues. So let me do it for the wave equation. Since I started writing this thing, I was doing wave equation, so I got carried away. So p of t and u of lt is g of t. This is for t greater than 0. Again, I am doing it for heat equation, Laplace equation. You can do it for heat or again, sorry. I am doing for wave equation. You can do it for Laplace equation or heat equation. No issues. So assume I want to solve it. So assume the solution u of xt should look like v of xt plus capital U of x comma t. Is it okay? This is what we are assuming. Now if you substitute it in this equation, yeah, the first equation, what do you get? You get vtt minus vxx is equals to h minus capital U tt plus c square plus capital U xx. Okay. Now what are the initial and boundary conditions? From the initial and boundary conditions, what you get? V of x0 is nothing but f of x minus capital U at the point x0, and then vt at x0 is nothing but g of x minus ut of x0. V of 0t is nothing but p of t minus u of 0t, and then v of lt is nothing but q of t minus u of l comma t. Okay, see, this is just a v. Now for this thing to work, we want this to be, as we have already talked about, we need it to be a homogeneous problem. So to make it homogeneous, we need this thing in such a way that p is equals to capital U and q is equals to capital U. If that happens, then what happens is v of 0t becomes 0. Is it okay? Right. So let me do it here so that I don't have to go. Okay. So now you see, we want to make the boundary conditions homogeneous. This is what we want, homogeneous. So if we want to make something like this, what happens? Capital U of 0t equals to p of t, capital U of lt equals to q of t. Okay, and u of xt it should be, see, this particular thing, okay, u of xx minus u of u, sorry, uxx plus minus utt, that part is there, right? So just a second, I did some mistake somewhere. No, it's okay, it's okay. Okay, so this is let's call this as maybe, what is the last number we did, 3, right? So let's call it a 4, right? So v of u of xt, you have to have this form, you see, pt plus x by l qt minus p of t. Is it okay? This is the form. So if you have this form, then you see the problem is you have to find that v of xt. Therefore, the problem, I mean, changes to this vtt minus c square vxx equals to h minus capital U of tt. Yes, h minus capital U of tt. So we are assuming that uxx, that part is basically 0. So that is how we got this problem. Okay, and then v of x0, yeah, this is nothing but f of x minus u of x0, which is, let's call it capital F of x, and then vt of x0, let's call this g of x minus u of ut of x0, which is g of x, and then v of 0t is nothing but 0, v of lt is nothing but 0. Now you know how to solve this problem, right? How do you solve it? So let's call this as capital H of xt. This problem we already know how to solve it. See, I did it for the wave equation, right? Exactly the similar sort of idea. So you solve this problem. So here what is the assumption? We assume that uxx is equals to 0. So with this assumption, this is what v of uxt you got with these boundary conditions. So you see, the thing is, what I'm trying to say is this: if you want to make these boundary conditions of this problem homogeneous, so I want to make these two homogeneous, yeah, this is the choice I have to take. That's what I'm trying to understand, explain. And once you do that, you have that v solves this particular star. So you solve v, and then once you solve v, you add it with u, and you are done. Is it okay? So this is how you solve this sort of problem. So with this, I'm going to leave this, end this course, and we are going to look at some problems which is related to this inhomogeneous boundary condition in the assignments. So thank you so much. Bye.